Well, good morning, dear. Welcome back. Uh, Today, actually, we're going to discuss about orientation representation. Orientation representation is very non-intuitive, and that's why it is troublesome to apprehend what is going on. Okay, so let us try to understand. But orientation representation is needed, otherwise we cannot control various devices. Sorry. Say for example, here this is a aeroplane, this is our hand, wrist, okay, and this is a robot wrist, and this is another robot wrist, okay. You know that orientation actually can be represented in the form of 3 by 3 rotation matrix, and that 3 by 3 rotation matrix has actually, how many elements? 2 1, 2 2, 2 3, or 3 1, or 3 2, or 3 3. That means there are 9 elements. And how many unknowns are there? 3 unknowns. Say phi, theta, and psi, reference to our this aeroplane. So we have 3 orientation. For that we have 9. For representing 3 independent coordinates phi, theta, psi, we have 9 elements, and that's problematic. We need to constrain it. But before going into any complexities, let us try to understand our our some kind of conventions which we follow for representing the orientation. We assign 3 orthogonal coordinate frame. Say this is known as roll, and roll normally is assigned with x-axis, and then this is your pitch is measured about y-axis, and yaw actually this is normally measured about z-axis. Okay, so for example, my wrist, that wrist also has been shown here. So consider a axis. About that, if I move my wrist, so this angle is called yaw. Okay, and then consider another axis. Okay, another axis perpendicular to the earlier axis. Okay, and if we move wrist in this fashion, this is actually pitch. This motion is described as pitch. Then consider another rotation axis on my wrist, which is mutually perpendicular to earlier 2, and I try to rotate like this. So this is known as roll. So yaw, pitch, and roll. These are the 3 orthogonal axes are assumed to be assigned on wrist, so that we can describe the orientation of the wrist. And this description of orientation of the wrist or the description of the orientation of the aircraft, or the so-called the description of the robot wrist, okay, they are extremely needed, because if we can describe, then that means if we can have a model, then we can control. Okay, so for a aircraft, so these actually angles are measured by sensor, and then by moving about those axis, you can control the orientation of the aircraft or wrist or robot wrist in a similar fashion in the 3D space. Okay, but in doing so, the fundamental problem is the orientation is actually non-intuitive. Say for example, here I have tried to draw a car, but it is, you will have to understand it, this is the front side of the car, and suppose this is a coordinate frame, body coordinate frame of the car moving in this direction, and from this direction car has rotated and came to this direction. So there is a orientation change. Forget about the position change right now, that is straightforward, we will describe it afterwards. But here you can see there is a orientation change of the car, and we would like to describe that orientation change uniquely, but unfortunately there is no unique way. There are innumerable ways, from orientation A to orientation B, okay, from orientation A to orientation B, okay, the car can attain that orientation into various possible ways. So that's a problematic, and we need to know that out of them uniquely how I can describe the car's orientation change. Okay. So here also this is roll, this is yaw, this is pitch, this is a robot hand, this is another robot, passive robot gripper. Okay. This is pitch, this is yaw, if you can rotate about this. Okay. And this is roll. So three motions are can be described by assigning three orthogonal coordinate frame, okay, on the body whose orientation you want to describe, and hence further you want to control. So seeing the non-intuitiveness of the representation of our 3x3 rotation matrix, we will study more deeply that what are the other ways of representation of orientation. But before that, let us try to deeply see what is our rotation, 3x3 rotation matrix is doing. Okay. As in our earlier lecture, we deduced that orientation can be represented. That means if you have a body coordinate frame and an inertial or fixed coordinate frame, then if the body rotates, that means the orientation of the body changes, then the body coordinate frame actually changes, okay, with respect to inertial coordinate frame. And then we have captured that rotation by 3x3 matrix. The one specialty characteristic feature of the matrix is all columns are mutually orthogonal with unit magnitude. Just you have already that matrix we have derived from the mother matrix all the basic matrices like theta, y, phi, and r, z, psi. So these are the matrices we have derived, and take any of the matrix and see that the columns are mutually orthogonal with unit magnitude. Column vector, this matrix has a column vector, this matrix also has a column vector, this matrix also has a column vector. They will have unit magnitude. Okay. And not only that, if you just first we are going to discuss, first say the body has undergone a rotation about its z axis by an angle psi, followed by another rotation about y by an angle theta, okay, and phi, sorry, this is phi, and so okay, psi, phi and theta followed by another rotation. So the body will ultimately, after undergoing 3 rotation, will reach somewhere, right? And where it has reached, you can just capture that orientation change simply by multiplying these matrices, but in order. Say if somebody has rotated first with respect to this and then with respect to this, then this is the third operation. Then, and if the rotations are all about the principal axis of the inertial coordinate frame, then the matrix has to be multiplied like this multiplied by this multiplied by this, and you will get a resultant matrix. We call it a composite rotation matrix. Okay, again it will be 3 cross 3, and even there you will observe that all the columns are of column vectors are of unit magnitude. Okay, and also the determinant of the rotation matrix is +1, and therefore it is called as proper orthonormal matrix. Okay, for example, this is just definition. You can verify that okay, this is whether this is composite rotation matrix is a proper orthonormal matrix or not by just simply assigning some values. Say this is 30 degree, okay, assign some value 30 degree, this is 45 degree, okay, and this is say 60 degree. So if you rotate, and you know the matrices, right, we have already derived. So now matrices are known, just multiply them and you will come across a composite rotation matrix, and you will see that the determinant of the rotation matrix will be +1. It shows that the rotation matrix is actually a proper orthonormal matrix. For non-proper orthonormal matrix, the determinant, okay, of that rotation matrix will be -1. As I said, each matrix has 9 elements, okay, 3 cross 3, but I have only 3 parameters, right, theta, phi and psi. So is there any way that I can reduce the number of parameters for representation? That's actually the problem looked into by Cayley by devising a Cayley's formula for orthonormal matrix, which states that any proper orthonormal matrix R, for any proper orthonormal matrix R, there exists a skew symmetric matrix S such that, so this is Cayley's formula, okay, such that the R will be equal to I is a unit matrix 3 cross 3 minus S inverse of that into I3 plus S. Okay. So this is his formula, and let us see what we are getting out of it. Since S is a actually a skew symmetric matrix, okay, that is S will be equals to negative of its transpose. That is the property of skew symmetric matrix. If you know, is fine. If you do not know, you can verify it. Okay, and here our skew symmetric matrix has to be of dimension 3. Okay, because our rotation matrix is of dimension 3. So then this matrix can be specified by only 3 parameters. Say one parameter is S suffix x, S suffix y, and S suffix z. Okay, and then S can be written as this is skew symmetric matrix. Okay, 0 minus Sz, then first row is is actually Sy, second row is Sz, 0 minus Sx, third row minus Sy, Sx, and 0. So we can see that any 3 by 3 rotation matrix which earlier for representation required 9 different elements, they can now be represented just using 3 parameters. Okay, that also we can actually, if we, instead of keeping the raw 3 by 3 matrix, if we just observe the nature of the matrix and put the constraint, necessary constraint, then of course we will be able to come across 6 such constraints, because ultimately I have only 3 independent parameters, theta, phi and psi, and R was having 9 elements. So we can constrain them appropriately. Say this is my 3 by 3 matrix, okay, and then I am so this is 3 cross 3 matrix, and I am writing like this. This is a column vector, x hat, y hat, z hat, where x hat is this column. Okay, this column is actually x hat. Similarly, y hat is this column. This is y hat, and this is our z hat. Okay, so so these are these columns, and then what you can see, that magnitude. So now I am putting constraint. You see there are 6 constraints now. You can check that determinant of this magnitude of this vector. Okay, R11, R21, R31. This one is 1. Magnitude, similarly magnitude of y equal to 1, magnitude of z cap equal to also 1, and then if, because this is orthogonal transformation, you can verify dot product between this vector and this vector will be 0, between this and this will be 0, between this and this also will be 0. So we got 6 constraints now. Okay, and then it's fine that although we have 9 elements, we could put 6 constraints to represent 3 independent coordinates, theta, phi and psi, because it only shows that they are these 9 elements are not independent, they are dependent, which is captured by this constraint. So that is, now I will try to give you a geometric representation of a rotation matrix. The column vector of vectors, this is actually column vectors, as you have seen earlier. This represent the principal axis, the vectors represent the principal axis of body coordinate frame. Okay, that is O, U, V, W with respect to inertial coordinate frame, and we can actually then we can actually draw the locations of all the principal axes of body coordinate frame. Okay, this body coordinate frame with respect to inertial coordinate frame. Okay. In other words, a rotation matrix geometrically represents the principal axis of the rotated coordinate system with respect to the reference coordinate system, which is not rotating, right? So this is a good geometric interpretation which clarifies actually what the 3 by 3 rotation matrix is. We can use now, let us just do some examples. Say on a body, say I have a body here, a rigid body. Okay. Okay. And this is my body coordinate frame. And here there are some points, say P. And this P is described, this is because this is U, V, W. So this is described with respect to U, V, W. Okay, position vector of P, say, is equals to 2, 4, 3. It's a column vector 2, 4, 3. Okay. Similarly, there are another points on this body, say, okay, there could be many actually, and whose position vectors are giving like 5, 3, 2, okay, with respect to the coordinate frame of body coordinate frame, okay. And since it's a rigid body, once these these points are described with respect to body coordinate frame, that's it. They will never change, okay, because the body is a rigid body and there is no deformation. So there is no question of changing the description of these points with respect to its own coordinate frame, that is body coordinate frame. However, now if the body is rotated, okay, say the body is now rotating, sorry about that, okay, so now the body is now rotating with respect to some of the principal axis of the maybe inertial coordinate frame, okay, this was our body coordinate frame, and there was some point P, there was some point Q, okay, and as I told, now body has rotated, okay, say, and there could be many rotations about x axis of the inertial coordinate frame followed by y axis of the body coordinate frame, that body can rotate, okay, and our objective is to track that rotation, okay. So how to determine P, that is when rotated, then its description change. So what is the changed description of the point P with respect to xyz coordinate, or what is the change of after rotation the point Q with respect to xyz, okay, if the body has rotated 60 degree about x axis. Don't worry about this, it could be anything, right, 60 degree about y axis or z axis, like that. So it's very simple. Since I know this rotation matrix, that is R x 60, okay, you already derived. So R xyz will be simply this multiplied by the rotation matrix, okay. Similarly, this will be this rotation this description of the body coordinate actually by multiplied by the rotation matrix. Now if we describe that, okay, my inertial coordinate, what is the rotation matrix actually is telling, it is the description of, we can also write like this, R is actually this, okay. That means description orientation R actually is capturing the orientation of body coordinate frame with respect to inertial coordinate frame, and once it is known, then just simply multiply the description of body, this cancel out, and then you get description of that point with respect to inertial coordinate frame. What if example 2, if I know the position and the orientation, I know the position, the point positions, okay, with respect to inertial coordinate frame, okay. Now my known parameter is P x y z this and Q x y z is this. Now how to determine P u v w, that means, and Q u v w, that is that point as seen from the body coordinate frame. You know that again you have observed that the relation between this and then this is what? In orthogonal transformation, this is the transpose of this, okay, this is the transpose of this. So, and not only that, its transpose is equal to inverse, we will discuss that, but you can verify it. So now I will have to multiply this with respect to transpose of the rotation matrix, and then I will get transpose of this matrix, okay, transpose of this matrix, then I will get, so it's very easy. So that is, transpose means this with respect to inertial coordinate frame, and now P you have with inertial coordinate frame, and what you need is description of P with respect to body coordinate frame. This cancels out, so P with respect to body coordinate frame is obtained when you just multiply this with respect to this, okay. I think this orientation representation will continue, is very important, since it has some non-intuitive behavior. Will go slow but steadily. You should understand how we are representing the orientation. Okay. With this, we'll introduce with the concept of composite rotation matrix, and then Euler representation of orientation, and then quaternion representation of the orientation in the next class. Till then, stay safe and have a nice day. Bye bye.